Welcome to the lecture for 6.3, volume by slicing. So up until now, we've been looking and using integrals and integration for two-dimensional graphs, the areas under a curve, etc. And so now with this section, we're moving into three-dimensional figures and figuring out volume as opposed to just area, and how do we do that? So in the past, again, we've seen that integration is used to compute the area of two-dimensional regions bounded by curves by using rectangles, two-dimensional rectangles, and the areas of those rectangles, and then adding them all together as the number of rectangles goes to infinity, if you will. Integrals can also be used to find the volume of three-dimensional regions or solids. And so we're going to use a similar method, basically slicing and summing, where we're going to calculate a cross-section area, as you can see in the top graph over here, and then add all of those together. So the slice and sum method we'll continue to use. So let's look at this figure a little bit closer. Consider a solid object that extends in the x direction from x equals a to x equals b, and imagine making a vertical cut through the solid perpendicular to the x-axis at a particular point x. And suppose the area of the cross-section created by the cut is given by a known integrable function. And that's that kind of like, it looks like a little archway. To find the volume of this solid, we first divide over the interval AB into n subintervals, just like we did for two dimension, of length delta x, which is b minus a over n, again the same thing. We now make vertical cuts through the solid perpendicular to the x-axis at each point, which produces n slices of thickness, delta x. Imagine cutting a loaf of bread to create n slices of equal width. And so now, before we were just counting the area of each rectangle. Now it's like, as they use the idea of a slice of bread, now that rectangle has thickness as we're slicing it through, and that instead of the delta x being like one of the width of the rectangle, that delta x now is, we have these shapes that we're slicing, and it's that thickness of the shape, if you will. So, where a rectangle turned into a box would be length times width times height. So the height in this case would be what we would be using as the delta x. And just as we saw with two-dimensional figures, as the number of slices increases, as n goes to infinity, and the thickness of each slice goes to 0, delta x goes to 0, the exact volume is obtained in terms of a definite integral. And here we can see the summation formula. But then basically what we're doing is, as the volume equals the integral from over the interval a to b of the area of x, a of x, times dx, and you can think of dx as the thickness of each of those slices. So the area times dx, which is the thickness. So let's look at our first problem. You might want to pause here, I understand this is the first problem. You might want to just watch what happens, because it does get a little bit confusing with some of these shapes that aren't familiar to us. So let R be the region in the first quadrant bounded by the coordinate axis, x and y, and the curve y equals 1 minus x squared. Okay? A solid has a base R, that's this base here that you see, and cross-section through the solid perpendicular to the base and parallel to the y-axis are squares. This is a square. Find the volume of the solid. Okay, so the area of the cross of the slice is what we're looking for. And here it's quite easy because the slice is a square. So the area of a square is it's this typical rectangle, length times width, but since they're the same, it's basically the side squared. Notice that the square has each side is the length of the formula, y equals 1 minus x squared. Here's a way to see it kind of almost in two-dimensional, somewhat three-dimensional. But notice each slice is a square with sides 1 minus x squared. So the area of the slice will be this formula squared, as I just mentioned. So that is what we're going to integrate. The integral from, again, notice we're going from 0 to 1 of 1 minus x squared, because that's side times side, length times width, they're both 1 minus x squared, dx. If we FOIL that out, we get the integral from 0 to 1 of 1 minus 2x squared plus x to the 4th dx. And this is a very simple integral that you should be able to solve. I'm not going to go into details on this one. And the answer is 8/15. Okay. So let's look at our next example. Example 2, volume of a parabolic hemisphere. A solid has a base that is bounded by the curves y equals x squared and y equals 2 minus x squared in the xy plane. Cross sections through the solid perpendicular to the base and parallel to the y-axis are semicircular discs. Find the volume of the solid. Remember, in all of these, what we're doing is we're looking for the area of the slice. And the slice here are semicircular discs. So a circle, a disc, has an area, a circle, has an area of pi r squared. Since they're semicircles, the area of each slice is 1/2 pi r squared. Now the thickness, again, of the bread is the dx in our integral. So the area is 1/2 pi r squared. A key point in this problem is to notice that the radius is half the distance between the two curves. Here it's kind of easy to see because you have a diagram, right? So we can see that the diameter is the full distance between 2 minus x squared and x squared. So the radius is half that distance, or 1 minus x squared. Okay? The other thing we need are the limits. So we have to find where those two curves intersect. Again, we can see it in this, but you could set these two curves equal to each other and solve for x. You could set x squared equals 2 minus x squared and then solve, and you'd get x equals the square root of 1, positive or negative square root of 1. So we get that the two curves intersect at plus or minus 1, and these are our integral limits. So if we set up our integral, we get volume equals the integral from -1 of pi over 2 times 1 minus x squared squared. So this is 1/2 pi r squared. This is very similar to what we did before. So the only difference here is that we're multiplying the whole thing times pi over 2 between -1 and 1. Again, a pretty simple integral to solve, and we end up with the answer 8 pi over 15. I'm assuming that you can solve this integral. It's a simple polynomial integral. The next thing we're looking at is something called the disk method. And this is just where you take a function, and you can see this function here, r of x, and then you rotate it around an axis. And this is known as a solid of revolution. So in the graph you see here to the right, if we rotated this around the x-axis, we wouldn't no longer have just this kind of quarter of a circle, but it would be a three-dimensional figure or a solid. And because we're creating it by revolving it around an axis, it's called the solid of revolution. So let's suppose f is a continuous function with f of x greater than or equal to 0 on an interval ab. Let R be the region bounded by the graph of f, the x-axis, and the lines x equals a and x equals b. In this next graph, you can see what it looks like as we revolve that function around the x-axis. As r revolves once about the x-axis, it sweeps out a three-dimensional solid of revolution. The goal is to find the volume of this solid, which may be done using the general slicing method. Now we have our volume formula here, and remember what we're looking for in terms of the area is the area of that slice, the area of the slice. And when you have a solid of revolution, the cross-sectional area has a special form because all cross-sections perpendicular to the x-axis, as you can see in the diagram here, are circular discs or circles with a radius of f of x, right? Because we revolved it, now we don't have to subtract it. The actual radius is f of x. The area of a circle is pi r squared. So for a solid of revolution, our area of that specific disk or circle is pi f of x squared, because f of x is our radius, as you can see in the diagram to the right. Because each slice through a solid is a circular disk, this is a special case of the general slicing method called the disk method. And so we get the volume equals the integral over the interval a to b of pi f of x squared dx. So let's look at example 3. Again, hit pause here if you want to try this yourself. The integral formula is here to the top. Hit pause and see if you can solve this problem. Let R be the region bounded by the curve f of x equals x plus 1 squared, the x-axis, and the lines x equals 0 and x equals 2. Find the volume of the solid of revolution obtained by revolving R around the x-axis. And here we can see the picture. So this is going to kind of look like a funnel on its side once you revolve it around. Excuse me. So we can see here our radius is f of x equals x plus 1 squared. Again, this is kind of a given in the formula for using the disk method for solving integrals or volumes of solids of revolution. Therefore, our area, again using this, the area of a circle, pi r squared, is going to be pi times the radius, which is our f of x, x plus 1 squared, squared. Okay? So setting up the formula, we get the integral from 0 to 2 of pi times our r, which is 1 plus x squared, squared dx. When we raise a power to a power, we multiply those exponents. And remember, pi is a constant, so we can take that outside. So simplifying the integral, we get the volume equals pi times the integral from 0 to 2 of x plus 1 to the 4th dx. If you remember back from Calculus 1, the way we would solve these is to use a substitution. And in this case, we can set u equals x plus 1. And then we get the integral of u to the 4th. Now remember, since we're changing the integral from x values to u values, then if x is 0, then u is going to be 0 plus 1 or 1. That's our lower limit that you see here on the right. And when x is 2, the upper limit, 2 plus 1 is 3. So when we evaluate the integral, we get u to the 5 over 5 times pi, evaluated from 1 to 3, and this gives us 242 pi over 5. Next, we're going to look at the washer method. This is a slight variation on the disk method, which enabled us to compute the volume of some more what they are calling exotic solids of revolution. So let's look at this. Suppose R is the region bounded by the graphs of f and g between x equals a and x equals b, and you can see that here, where f of x is greater than or equal to g of x, which is greater than or equal to 0. If R is revolved around the x-axis to generate a solid of revolution, the resulting solid generally has a hole in it, and you can see that here in the core of that around the x And that's that distance right here between g of x and the x-axis. There's nothing there. It's a hollowed out part. So in this case, a cross-section through the solid perpendicular to the x-axis is a circular washer. So we still have a circle, but it has an outer radius of r sub 0, which is the f of x, and an inner radius, which is close to the center, of g of x, where a is less than or equal to x is less than or equal to b over that area. So we can see here that the area of the cross section is equal to the area of the entire disk minus the area of the hole. And so this is really easy because with two expressions, the radius of the outer disk is going to be f of x. The radius of the inner of the hole is going to be g of x. And so we have pi, or the outer radius squared, minus the inner radius squared, which equals pi times f of x squared minus g of x squared. So it's very much similar to the disk method. We're just subtracting out the volume, or excuse me, the area of the hole before we enter. So let's take a look at example number 4, finding the volume by the washer method. And remember that the volume equals the integral over an interval of pi times the outer radius squared, which is the function that represents the outer radius, minus the function that represents the inner radius squared dx. The region R is bounded by the graphs f of x equals the square root of x and g of x equals x squared between x equals 0 and x equals 1. What is the volume of the solid that results when R is revolved around the x-axis? So often in these, you've been giving images or graphs of these. Finding the graph is important to know which of the function is on the outer side and which is closer to the x-axis over that interval. And so here we can see kind of a two-dimensional figure where we can see that f of x is further away from the x-axis than x squared. This is similar when we were trying to find the area between curves, the upper curve minus the lower curve. So we're kind of using that same kind of thought here. What's nice with these graphics is you can kind of get a picture of what the shape would be. And in this case, when we take this and revolve it around the x-axis, we actually get a kind of a bowl shape here. Okay, so we can see that, again, f of x is the outer edge or the outer radius, and g of x is going to be the inner radius, which is similar to our form. So we have the integral, the volume equals the integral from 0 to 1, which is our interval given in the problem, of pi times the outer radius squared, which is f of x, the square root of x squared, minus the inner radius, which is g of x, or x squared squared. If we simplify this, we get, we pull the pi out because it's a constant, the integral from 0 to 1 of x minus x to the 4th dx. This is a very simple integral. When we integrate that, we get x squared over 2 minus x to the 5th over 5, evaluated between 0 and 1. Sorry about this bracket. I don't have any kind of symbol that I can use that allows me to kind of do the straight line, if you will, that's equal in size here. When we evaluate this integral over these limits, we get 3 pi over 10 for the volume of this bowl, if you will. Okay? So far we've been evaluating solids that revolve around the x-axis. But what happens if the solid revolves around the y-axis, as you can see in this image here? Well, everything you've learned about revolving around the x is really the same as revolving around the y. It's just that we're going to use functions that are defined in terms of y, as you can see here. So the outer radius would be x equals a function p of y, and the inner radius would be a function x equals q of y. Again, we're going to have a washer or a disk, depending upon whether we have two functions or one and revolve around the axis. But here we can see that the area is going to be the outer function squared, pi r squared. That's the area of the outer disk minus the area of the hole, which is q sub y squared, right? Pi q sub y squared. And so we have a very similar formula as we did when we revolved around the x-axis. And so the washer method really looks pretty much the same, except we have functions in terms of y instead of in terms of x, but it's the same thing. Pi times the outer radius squared minus the inner radius squared, dy over whatever interval. Notice if we get rid of q sub y, or make that equal to 0, then what happens is we just have the disk method, which would be, there would be no hole here. This would just be a big solid spherical type looking thing with a flat top and a flat bottom between C and D. So here we would just have pi, the function squared, which we saw is the disk method. So let's look at example 5. This is a great example because what we're going to do is we're going to take two equations and revolve it both around the x and around the y axis. So it's kind of a cool problem. Let R be the region in the first quadrant bounded by the graphs of x equals y cubed and x equals 4y. Which is greater, the volume of the solid generated when R is revolved around the x-axis or the y-axis? Well, let's figure out where these two graphs intersect so we can find our limits both in terms of x and y. And we do that by setting the two equations equal, x equals x, or in this, x equals x, which means y cubed equals 4y. If we set this equal to 0, we get y cubed minus 4y equals 0, and factoring out a y, we get y times y squared minus 4 equals 0. So we can see that this is true when y equals 0 or when y equals 2. Okay, remember we're only dealing in the first quadrant, so we don't have to consider negative 2 here, because these are solids of revolution. So they have to be in one quadrant then to revolve all the way around. Okay? So let's first look at the y-axis revolution, since we have the equations defined in terms of x equals y cubed, etc., and x equals 4y. So our outer function is going to be y cubed minus the inner function, which is 4y, and the y values that we're going to integrate on are going to be between 0 and 2. So of course we have pi outer radius squared, 4y squared, minus inner radius, y cubed. And I said that wrong, and so I'm going to leave that in the recording. I said that y cubed was the outer radius. And this is a very common mistake. I'm so used to looking at the upper equation and the lower equation, and that would be true if we were rotating around x. But we're rotating around y, so we're looking for the outer equation, which is the furthest one away, which is not y cubed, it's closer to y. So I had these backwards. So that's a great mistake for me to make in your lecture, because it's a common mistake that we don't slow down enough and say, oh, well, look, here y cubed is on top, so that's the outer function. It's not on top if we think about left and right, which is further away from y. So again, I'm going to leave that there, and hopefully you can learn from my mistake there. So now it's just a process of integrating. Again, remember the functions are the radius, so they're squared, pi r squared of the outer function minus the radius of the function, which is the radius of the hole. And here's a good diagram of it so you can see it now as well. You kind of see the two-dimensional graph kind of embedded in there. And let's finish integrating. Or simplifying first, 4y squared is 16y squared, y cubed squared is y to the 6th squared, and if we integrate this over 0 to 2, again using the y values, 0 and 2, that's very important here for the limits of integration, we get 512 over 21. Not a very difficult problem. Again, when you're dealing with y revolutions, for me, I'm so used to doing x that it's easy to get confused about which is the outer and which is the inner, so just slow down. Now let's look at the x-axis revolution. Well, the first thing we need to do is redefine these equations so we get y equals some function of x. And when we do that, we get, in the first equation, y equals x to the 1/3 or the cube root of x. And in the second equation, we get y equals x over 4 or 1/4 x. Here are the diagrams, and we can see that when we graph them, now I'll see it, x to the 1/3 is the outer function, and x over 4, or 1/4 x, is the inner function. And again, going back to the values, I didn't have them on this slide as well, but the x values are between 0 and 8. So we can see that we're going to integrate between 0 and 8 of pi times the outer radius, which is x to the 1/3 squared, minus x over 4 squared dx. Again, now we have dx, and the other one we had dy. Make sure you're using the right notation. Simplifying a little, pulling the pi outside since it's a constant or coefficient, squaring x to the 1/3, squaring x over 4, we get the following equation. And when we solve this, when we integrate it, I'm not going to go through the integration there. The setup is the most important part. You should already know how to integrate. Both of these are power functions, so it should be pretty straightforward. So when we integrate the volume around of the solid revolving around x, we get 128 pi over 15. And remember from the last slide, when we revolved around y, we had 512 pi over 21. So our y revolution has a greater volume here. Example 6 is a really interesting problem, and while I'm not going to go through the entire example, it is in your text and I highly recommend you look at it. I am going to walk through the setup of each of these problems. And this is when we're revolving around other lines, not the axis, not the x or the y axis. So we have three different problems. They all use the same functions, f of x and g of x. And we have different revolutions. So this first problem, A, is just the function f revolving around y equals 2. And you can see that here. Here's where we're revolving around. There's our function f of x. Okay. And we're revolving around up here. Now normally we would revolve around the x-axis, and the radius would simply be our functional value, the distance from the x-axis to the function. But since we're revolving around 2, now our radius is the distance from our function to that horizontal line y equals 2. So it's going to be the difference between 2 and our functional value. Then you can see that here. So we'd have 2 minus the square root of x plus 1 in parentheses. And that gives us a radius of 1 minus the square root of x. This problem also, like sometimes intuitively, I would think it is a washer problem because it looks like there's a hole here. But remember, we're not revolving around x, we're revolving around 2. So there is no hole. This is simply a disk problem. And so we get the integral of pi r squared, or the area of a circle or a disk. All of the intervals of integration were given, so I'm not going to talk about those. You can see them here. They're labeled on the graphs, etc. Okay. Our second problem here is using the region bounded by f and g that revolves around y equals -1. Now this is an interesting problem, and when I first tried it, I actually got confused on this because I can see that I'm 2 units away, right? It intersects at 1 and then it goes to -1. But remember, when we're doing washer problems, the functions are the distance. The y is the distance from the origin. So we're not dropping down by 2 units from 1 to -1. We're really only dropping below the origin, or excuse me, below the x-axis by 1 unit. So in all of these problems, we have to add, the radius is, the normal radius is the function, so it's from the graph, the outer function, which is the square root of x plus 1, to the x-axis. And now we need to add another unit of 1 for this distance, which will be the new radius. And so we get the square root of x plus 1, which gives me the square root of x plus 2. And then the inner radius is x squared plus 1, again, plus another 1, so it'll be x squared plus 2. And so here we have a washer problem with the outer radius, the square root of x plus 2 squared minus square root of x squared plus 2 squared. Okay. So pi r squared minus pi r squared. Yeah, we're good. All right, so the last problem is f and g revolving around x equals 2. Now x equals 2 is a vertical line, so this is similar to when we're revolving around the y-axis. So we're going to have to solve our problems for x equals a function of y, and then also, again, the intervals are given. So here's our problem, here's our graph, excuse me, and we're revolving around x equals 2. So in this case, the radius is going to be from 2. Normally the radius is just this distance, but now we're going to subtract the distance from the y-axis from there. So we have 2 minus the functions, whether it be the outer radius or the inner radius. And you can see that we're going to, because the radius is now from that function all the way to 2, so it's this line, x equals 2, minus these functional lines. And so again, when we subtract this, we get the outer radius is 2 minus y minus 1 squared, because the function was y minus, when we solved it, it was y minus 1 squared. The inner function is x equals the square root of y minus 1, so this is 2 minus the square root of y minus 1. Now be careful here, because again, intuitively you're used to revolving around y, and so now this, if we were revolving around y, what would have been the outer radius has actually become the inner radius, because we're revolving around x equals 2. And so here's the function that we would set up for that. Once you have these setups, it's easy to solve these integrals. Just take your time and focus. But you can see it's really important to look at the graphs and kind of visually see where the radius would be from your axis of revolution. Y equals 2, y equals -1, and x equals 2. And then figure out what's the radius from there to the function. What's the distance from that line or axis of revolution to the function, whether it be a disk or whether it be a washer where you're going to have two different measures.